Now, on to the next speaker. Athira Menon works at the University of Amsterdam, and she has a presentation with the title, How Well Do We Know Our Stars? So, over to Athira.
Yes, thank you. Let me start by sharing my screen.
That sounds good.
Okay.
Yes, your screen is popping up.
And I will minimize my window. Okay, well, I'm guessing now everyone can hear me.
Yes.
Good afternoon, everybody, and thank you for this amazing opportunity indeed to speak to you all today, especially under these circumstances. So thank you all for being there. I'm a theoretical astrophysicist at the University of Amsterdam, and today I'm going to speak to you about how well we really know our stars. Let me take you to the year 2015. It was an especially historic one in the records of physics because it was in this year that we realized we understand gravity quite well. LIGO had made its first ever detection of gravitational waves, those ripples in space and time caused by the motion of two objects going around each other. The waves which LIGO detected came from a pair of black holes a billion light years away, moments before they collided and merged to become a single black hole. In 2017, the Nobel Prize in Physics was awarded for this very discovery. And since then, LIGO has detected 12 such merging events. Now, while generally physicists were quite relieved that, oh, well, we understand gravity quite well, astrophysicists were asking a different question. How well do we really understand the stars that ended up as these black holes? Stars are, after all, those fundamental building blocks of the visible universe. In fact, a massive star that's over 10 times heavier than the sun is responsible for producing almost 70% of the elements in your body. When such a massive star nears its end, it expands, collapses, and then explodes as a supernova to finally end up as a black hole. So it's intuitive to think that if you were to form a pair of black holes going around each other, it may have come from a pair of stars that went around each other. We call these binary star systems. Now, the black holes which LIGO detected came from old galaxies, billions of light years away. So if you were to understand the kind of stars that created them, we need to look for an environment which is A, having a similar chemical composition as those old galaxies, and B, is close enough to us so we can make precise measurements of their stars. Fortunately, nature has been quite lucky to us. She gave us two such galaxies. These are called the Large and Small Magellanic Clouds, which you see in the picture right there, and they're satellite galaxies of our own Milky Way. Now, these are old dwarf galaxies which were pulled towards the Milky Way by its enormous gravity sometime in the distant past. Now, we are doubly lucky because these old galaxies are still forming new stars, which means by observing them, we can study how massive stars are born and observe them all the way until they die. Now, in particular, in the Large Magellanic Cloud exists a region called the Tarantula Nebula, a nursery of stars. This region has been studied quite well by the Very Large Telescope and is found to be rich in a diverse population of massive stars. But what took us by surprise really was how most of these stars are found to be living in binary systems, some of them so close they could end up making the very black hole pairs we are interested in. Now, just as in human couples, star couples also lead complicated lives. In fact, the closer they live, the more complicated their lives are. While human beings do this by talking to each other, stars do this by transferring mass to each other. If you were to start with a pair of stars that went around each other every 3 days, tidal forces like the ones that exist between the Earth and the Moon will end up bringing them closer. At some point in their lives, both stars will expand almost simultaneously and converge at a common point in between them, through which they transfer mass back and forth and thereby exchange a cosmic kiss, if I may, which lasts for a few million years. Now, this phase is called the contact phase in binary stars and is a telltale signature of such close binary systems which we are interested in. From there on, the stars can either shrink, detach, and then go on to evolve and die as black holes, or they can merge while continuing to expand finally into a single massive star that rotates quite rapidly. So any stellar model that attempts to find out how black hole pairs are made must be able to explain all the features of this very important contact phase in their lives. And that is the precise aim of my research, where we are trying to see if our present day models of binary stars can explain what we observe in the Tarantula Nebula using contact binaries. Now, there are 5 such contact binaries so far that we have found in the Tarantula Nebula. And now let's go about seeing how we can go about modeling a binary star system. To do this, we start with 3 main inputs, which are the masses of the 2 stars and their initial orbital period. This is then plugged into a 1D stellar evolution code, which assumes that stars evolve spherically. And we start their evolution from their birth and follow it all the way until they either merge as stars or collapse into black holes. After that, we take the output of our code and compare it with what we see. For the purpose of this research, we built a grid of nearly 2,000 binary star models comprising a range of initial parameters. We then took the contact binaries from them and compared it with what we observe in the Tarantula Nebula. So let us see how well our models do. Now, what we predict from our models is that the most common contact binaries must have equal masses for both the stars. And this is verified by what we observe in the Tarantula Nebula as well, within the uncertainties of the measurements. But from there on, there seemed to be quite a bit of a difference. We expect at least 7 times more contact binaries to exist presently in that nebula. And not only that, the majority of them must be less massive and have shorter orbital periods than what we are presently observing. So what our models are telling us is that we should be expecting to see a lot more contact binaries, and the ones we are seeing right now must be the rarer ones. So clearly there is a discrepancy between our models and what we're observing. We don't seem to be quite there yet. So what could be the reasons for that? Well, one of the most uncertain phenomena of which we have a very basic understanding at best when it comes to massive stars is their rotation. Massive stars are found to be fast rotators, going up to hundreds of kilometers per second at their equator. And we expect that these massive stars must have meridional circulation currents inside them, just like the ones in our oceans, which take material from under the surface and bring it towards the surface. Now, depending on the efficiency of this mixing inside the star, a closed binary system could end up merging while it's still stars, or they could evolve all the way to merge as black holes. This uncertainty, this efficiency uncertainty of mixing, is presently the work I am pursuing in my research as well, to see how it impacts the evolution of massive stars generally. Now, perhaps there is a problem from the side of the observations as well. Maybe our sample size is a bit too limited for the purpose of our study, and hence we should continue to observe this region and others like it in more detail and continue to tally between our models and our observations to see how well we understand things. Now, how do we tie it all up back towards gravitational waves? How well can we take this work forward? Well, in the future, in the next few years, in fact, LIGO will be upgraded so that we end up detecting black hole and neutron star mergers one every few hours. And soon enough, LISA, a space-based gravitational wave detector, will be launched, and it will be able to detect all sorts of mergers in the local and distant universe and increase this population of merging events. Now, we are truly going to face an astronomical flood of data in the coming decade, and we are equipping ourselves by making predictions of the kind of detections these instruments will make. For this, we cannot just make a simulation of a few thousand models. We need 10 million binary stars to do this. And to do this within a reasonable amount of time, we need to simulate them with simplified models so we can do it in the human span of life. And these models are themselves based on the detailed ones I presented in this work. But we just learned that even the most detailed binary star models cannot explain an important phase of the lives of the kind of stars that will end up making black hole couples, which LIGO and LISA will detect in the future. It is thus especially crucial in this era of astronomy that we understand how stars, the most fundamental units of our universe, work very well and their physics. My message thus for the future of astronomy, this data-intensive era, is that let us continue to test what is known and visible in the local universe before and while seeking what is unknown and invisible in the dark corners of the distant universe. Thank you very much.
Wow, thank you so much, Athir, for that final beautiful set of sentences. Very, very amazing talk. Thank you so much. It's great. We went from atomic connections and more connections are needed to the relationship between stars, and that basically we went from meta atoms to the atoms of the cosmos being the stars.